Here we have a third sample problem. We have a rectangular loop shown in blue here. That's a rectangular loop of wire immersed in a non-uniform magnetic field. So we have a non-uniform now magnetic field. Before, in previous problem, we had a uniform magnetic field, changing with time, but uniform. Here we have a non-uniform magnetic field. Okay, the field magnitude is given by this 4t squared x squared. So why B is non-uniform? Is it because it depends on t time, or is it because it depends on x? Well, it's because it depends on x. Non-uniform, it means non-uniform in the space. If you are here, if you are here, if you are here, the field is different. For at each time, let's say t equal 1 second, B here and B here and B here, they are different. B is expressed in Tesla, T is in second, and X is in meter. Okay. The loop has a width W and height H. Right? Given. What are the magnitude and direction of the induced EMF around the loop at T equal 0.1 second? So always we start with magnitude. Let's start with direction now. So B, where is B? Is into the board. Okay, B is into the board. So let's use Lenz's law. Initial B into the board. Flux increasing or decreasing? Well, B times the area, so this is increasing. Where is the induced flux now? The induced field now, sorry. The induced field should be out of the board. It fights against this increase. So where is the current, or where is the EMF? B is out of the board, B induced. Okay, so where is EMF? The EMF should be in this. The current induced in this direction, so the EMF is in this direction. That's the induced EMF. Induced EMF is counterclockwise. Counterclockwise this time. Now magnitude. What about the magnitude? Well, the magnitude, as usual, we will use Faraday's law. E equal number of the loop. We have just one, so that's 1 d phi over dt. Okay. Now what is the flux? Well, the flux, we have a non-uniform field. So the flux is integral of B dA. B dA. Okay. B, we know it. So what is dA? We took a dA, a rectangle like that, a rectangle of width dx and height h. Why we took this? Because look at the expression of B. B is changing with x, or it's changing with y? B is changing with x. It means if you take this point, and 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 this point at the same y, B is changing or no? No, B is constant. If you take a line like this, all these points have the same magnetic field. So the variation of magnetic field doesn't depend on the y, so it depends only on the variation of along x direction. So that's why a reason we took a rectangle like that, h in y direction, that's the height, total height, because B is invariant here, and dx, because B here, it varies along x direction. So here we assume that we have, if I take an element area like that, a rectangle like that, I will assume that I have the same magnetic field, because dx is very, 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 very small. It's like a point, right? So my area, what it will be? The area of a rectangle, that's the height, times the width is dx. So I will replace now. B is 4t squared x squared, and we have h and we have dx. Constant out from the integral, 4h t squared all these are constant, and we have integral of x squared dx, would give you 4h t squared x cubed over 3. It varies from where to where? From 0 to w. So the flux is 4h w cubed over 3 t squared. If you replace h and w with their value, you will get here 72 t squared. Now the EMF is derivative of the flux, so I need to derive that. So I get 144 t. Now we need the EMF at t equals 0, 1, so you replace that, and you get an EMF of 14.4 volts. So that's the magnitude, that's the direction, and that's the solution of this problem. Let's say we don't have this hint of this element area. We don't know which element area I need to choose. And I need to calculate the flux. So the flux, that's the integral of BdA. Okay, I know the formula for B, but what is dA? Well, dA, since I have x and y, dA, what is it? That's dx dy. And what we will be using here is double area integration, because I am integrating on the surface, on the area of the loop. So I need to integrate along x vary from 0 to w, and I need to integrate from y vary from 0 to h, of what? Of b, which is 4t squared x squared dx dy. I need to integrate first with y. All this is constant, so it will be integral from x equal to 0 to w, 4 t squared x squared, all these are constant, doesn't depend on y. Integral from 0 to h of dy. Integral of 0 to h dy, what it give you? So dx. Integral of from 0 to h of dy, that's h. So you get integral from 0 to w, 4 t squared x squared h dx. And this we come back to the previous result. We have 4 t squared h here, integral of x squared dx. That's exactly what we found before. So you get 4 t squared h, integral of x squared, that's x cubed, so x cubed over 3, so you have w 3 over 3. Okay? Let's solve now this checkpoint on inductor. So here in this inductor, okay, shown like that in circuit, we have the EMF. The induced EMF in this coil is in this direction. Okay? So which of the following can describe the current through the coil? So we have a current through the coil, and because of that, we have an induced EMF in this direction. So what are the situations that we have? Can we have a constant current rightward? So current going to the right, and it's constant. Well, if the current is constant, we don't have an induced EMF. Induced EMF, it comes from the change of the current. So this is to rule it out. Constant and leftward, same thing. We have a constant current, there is no EMF in the coil. Now, current is changing here, increasing and decreasing. So let's take a situation C. We have a coil, and we have a current in this direction. And the current, so the current is this direction, and the current is increasing. But there is a rise of current. What is the direction of the EMF? The EMF, it should oppose this increase. So that's the direction of the induced EMF. So this is not the situation. So this to rule it out again. Decreasing and rightward. Okay, let's draw this situation. D We have the coil here, or the solenoid. The current is rightward, like this, but the current is decreasing. The current is decreasing. The EMF should find this decrease, so it should raise the current. So the EMF should be in this direction. That's this situation. So this is a possible explanation. Let's move on. Should not stop here. Maybe there is another possible situation. E. We draw the EMF, and we have a current leftward. So the current is coming in this direction. That's the direction of the current. What happened with the current? This current is increasing in this direction. What we do the EMF, it will oppose this increase. So by creating another current in opposite direction. Okay, that's the situation. So this is also okay. So D and E, they are possible explanation. Let's see now F. We have the inductor. The current is toward the left. Fine. And the current is decreasing. We have a decreasing current toward the left. The EMF should fight this decrease, so it should increase the current. How? By being in this direction. So this is not this situation, so we should rule it out. That's the solution of this checkpoint. Then this is a sample problem on inductor circuit, and here we have in the figure a complex inductor circuit. So this is not a simple RL circuit, that's a complex one. And in this figure, we have a circuit that contains 3 identical resistors. So the resistors are the same here, R and R. Resistor R equal 9 ohm, and 2 identical inductors. So we have the inductance here, L equal 2 millihenry, and we have an ideal battery of EMF, 18 volt. What is the current, I, through the battery just after the switch is closed? So when we close the switch, what is the current through the battery? We want the current through the battery. All right, so how will we solve this problem? So just I remind you, we solved it something similar in RC circuits. So in RC complex circuits, and we said there are 2 ways how to solve this kind of situation, either by using Kirchhoff rule, okay, to get the differential equation and solving it by comparison, and from that we can solve different questions that we are asked, or by equivalent circuits by looking at two characteristic points, t equals 0 and t equals infinity. So in this situation, it's better to see the equivalent circuit. Why? Because we are asked about what happened just when the switch is closed. Switch is closed, it means t equals 0. Alright, so the characteristic of the inductor, when we close here the switch, what will happen? There is a current raise. So the current, it was 0, and it starts to increase. The current in the inductor, EL. Current, it was 0, and it starts to increase in this fashion until reaching an asymptotic value. That's what we have seen in the lecture. What will interest us here, what happened at t equals 0? We have a current equals 0 on the inductors. What it means, the inductor will behave as what? When the current is 0, I is 0, the inductor is like a broken wire. So I can draw the same circuit but by replacing the inductor here by a broken wire. So let's do it. We have a broken wire here, we have a resistor here, we have this resistor here, and we have a resistor here and broken wire here. So that's the equivalent circuit. Well, we can simplify it again because this resistor and this resistor, there is no point to draw them. There is a broken wire here. So it will be as simple as that. We have this resistor in the middle here, and we have the battery. And the question, what is it? What is the current in the battery? Well, that's very easy now. I equal E over R. So it gives you 18 divided by 9, just 2 ampere. That's the current on the battery when we just close the switch. The second classical question is the following. What is the current through the battery long after the switch has been closed? What it means long after the switch has been closed? T equal infinity. Okay, current in the inductor, what is it? Infinite current, 1 minus exponential minus T over tau. And we know tau. What is the voltage across the inductor? We said that dIL over dt, okay, that's a constant, okay, exponential minus T over tau. V naught, let's say. Well, in a simple RL circuit, I naught, I infinity, that's just E over R, and V naught, that's E. But in a complex circuit, that's not the case. But what we can see, so the current starts from 0 and goes up, raise up. What about the voltage? The voltage starts from a certain value and decrease exponentially. What is the value of the potential at T equal infinity? VL equals 0. Now we have inductor, and we are saying that VL is 0. What it means, these 2 points, they have the same potential, so I can replace them with a wire. So the inductor behaves as a closed wire. Well, we draw it like this. We have a resistor here. Inductor, replace it with a wire. We have a second resistor here. And we have a third resistor here. So the 2 inductors, you replace them with what? The 2 inductors, you replace them with a wire. And we have the EMF. Now let's read the question again. What is the current flowing in the EMF? Well, that's simple circuit question. So the equivalent resistor here, what is it? That's R over 3. You can figure it out yourself. So it's like we have R over 3 here and the EMF here. So what is the current now? The current, we can, on the battery, that's E over R over 3. So that's 3 times E over R. So that gives you 6 ampere. Thank you for watching. See you in my next video.